So for grid search, what we will do here basically is I think I kind of mentioned in the DB scan, it's like basically you want to try out many hyperparameters. So what's kind of cool is that when we do a machine learning algorithm, right, essentially, a lot of times you don't know exactly what the good hyperparameters are. And I think XKCD perfectly like encompassed like this in kind of like this idea where essentially like you kind of try things out, and then if it doesn't quite work out, you kind of like just mess around with the dials, essentially, these hyperparameters, and just see if it works better until it basically looks like it predicted better. That's kind of like machine learning in a nutshell sometimes, at least that's how it feels at times. And note that basically you can think of these hyperparameters, right? So think back in DB scan when we had, what's it called, like epsilon and min number of samples. Basically, these are like different dials you can adjust. And you can imagine like trying to adjust all of these dials can be like really annoying. Like you can imagine like trying to adjust each one manually, like we were playing around with DB scan. Can take a lot of time. So we can automate this process. So that's where grid search kind of comes in. So grid search is actually another part built into scikit-learn. And there's a few ways we can actually use this to like basically say, all right, here's all the different hyperparameters that I can try out. Go ahead and run this. Now I will say grid search isn't the only way to search for things. One example is actually using random search. But grid search will basically go through every combination of the parameters you give it. Where random search might just go on a spectrum and try to randomly kind of pick things out. Sometimes you might want to use random search. Sometimes grid search might make more sense. Okay, so a good thing to kind of try out. So a basic grid search thing, just kind of show you what this looks like. Note that you still have to import this. I'm just kind of just a quick code snippet. Basically, you pass in parameters. So imagine this is for a support vector machine. We pass in a kernel and say, all right, for this dictionary of parameters, say kernel can be either be linear or RBF, so radial basis function, or C, or test out these parameters of C of 1, 10, and 50. And if there's any other parameters that are like built into like that model and you don't specify it, they'll just use the defaults, okay? So you see our classifier, we just build it like our normal case with no hyperparameters or anything like that. So we just click the classifier, and then we actually have our true classifier here, which will actually be the grid search right here. And basically pass in whatever classifier, whatever model you want to pass in. Note that this can also be a pipeline. You can pass this directly here and then pass in the parameters. And basically grid search now will actually do cross-validation with grid search CV. We'll actually do cross-validation by taking whatever data you put in, say xtrain, it will do cross-validation in there for you. So you don't have to actually worry about passing this in yourself. And basically it will go ahead and fit this across here, and it'll return basically all the different models and how well they perform with this Y train right here. And basically you can then decide, you know, which of those models work best. And you can also go ahead and test this onto your, let's say your X test, and see how well that performs and evaluates. So this is a really efficient way to like automate this part. Note that it still has to basically train every model, like every type of model with a different hyperparameter. So you can see here we have 2 kernels and 3 C parameters. This will end up being 6 different models that it have to train. Okay, cool. Okay, makes sense? Any questions on that structure? No. Okay, cool. So this is where the bad search comes through. So this is where like pipelines in particular are really useful. So one thing, like I said, is that grid search CV will do cross-validation, which is good. We want cross-validation. Let's just see the whole set and also do validation over it, right? So I'm going to show you the wrong way to do this, or the way that would create data leakage, where it would see all of the data set of the X train. And that basically means it knows the validation set before it even like does the validation. And that's not what we want. So, and this will look really innocent. This doesn't look like anything in particular. We have our scalar, our scale data. So note that basically I have our scalar here, and then I'm going to scale the data over X train. This is where the data leakage comes through, is that if I scale it over the whole X train now, when it does cross validation, what's going to happen is that it's going to see all of the data for X train. We're in cross validation. Remember, we take our X train, say, here's our training set and here's our validation set. The problem is now is that it's going to see all of that information at once. It's going to kind of encoded within the information, and there's potential for leakage. And it might not seem like really major, but there's some really weird things that can happen with ML stuff when you start having data leakage from like your test or validation sets. So note that basically that's the only difference between this top and bottom one here. And basically this scalar is the thing that leaks out this information. But you can say, but you know, Victor, I want to use a scalar. Like I need to use this for my data set. Like it's not going to work. Like how would you do this, right? With grid search, like it seems like it's kind of like not something you can do. And kind of, yeah, it's not really easy to just pass in through grid search right here, but there's a solution. So what we can do instead is actually pass in a pipeline instead of the whole actual classifier here. So this classifier, this pipeline, is going to be like our new classifier, our new support vector machine. But this classifier, or this pipeline is going to include the scalar. And what's going to happen now is that basically it's going to train on this scalar, or sorry, this model, essentially this pipeline, instead of the support vector machine itself. So what's really cool about that is that you don't have to worry about that data leakage coming out here, and it'll actually scale each part. It basically will feed this every time it does cross-validation. And so this helps you prevent that leakage going through. And so again, this is like really subtle stuff where like you can see it's not super clear that this would actually be leaking information, but in fact it does. And so that's why you have to be very careful. And this is where pipelines can make kind of processing that whole steps of whatever you're doing, putting into one nice neat little package, and you pass the package off to grid search, and grid search will take care of the rest. Cool. All right. So, and you can see basically essentially no change from like this part, other than the fact that we just passed in the pipeline. Okay. Any questions? Cool. Nice. So again, another reason why using pipelines are really useful. And this is where, again, I will mention about leaking information, and then we'll kind of, I think we'll call it right here. But there was an example of this, I can't remember how long ago it was, maybe a few months ago. They were doing something called an adversarial neural network. And essentially the goal of this model was basically is say, okay, take this thing that is, I think it was like a satellite image, like Google Maps or something like that, took in the satellite image. And its goal was to take a satellite image and pass it into a basically make it more cartoonish, you know, kind of from that, just purely looking at the image, create a cartoon kind of image for the navigation. And then what it would do, adversarial, it would take that cartoon and convert it back into something that looked like more like a satellite image. And so the idea here is like, you know, can we basically take something that's a cartoon image and convert it into a satellite looking image? So like more realistic and stuff like that. And so it was an interesting project. And what they found was really interesting. It did actually a really great job, but they started noticing really weird stuff where they test out the testing set, and they said, here's a testing set with the real satellite image. And then they would have a cartoon image of it. And then they would have like the final image. And the final image looked almost exactly like the original testing set. And what's interesting is that there were some things like buildings would disappear from the cartoon image, but would reappear in the final image. And they're like, what's going on? And they found out basically this kind of data leakage is that essentially what was going on is that the model learned, and I won't go into full details of like how it does this, but basically it learned to take the information from the satellite image and encode it in the noise of the pixels of the cartoon image. So like there were little pixels basically with like extra information that really we as humans just can't see or notice, right? But they were there, and was encoding information and then taking that information and basically recreating that part. So essentially it was knowing what the answer was before it was ever tested. So those are kind of things where like you can get these weird cases where like machine learning models are really good at finding a way to like get the right answer. So if you give it a shortcut, like if you leave like essentially the answer key on your desk, the machine learning algorithm, you know, kind of learning stuff, it's just going to cheat up and look at the answer key. So you know that kind of like these are some interesting things that can happen. So always be really careful about data information or leakage, data leaking information. Okay, cool. All right, so yeah, any last questions? Pretty cool. Okay, I will stop it here.